Hi everyone. In this video we're going to be talking about exponential and logarithmic equations. So first off, what is a logarithmic function? So we have worked with exponential functions prior to this topic, and I want you to consider these three exponential equations. So we have 4 to the power of x equals 16, 2 to the power of x equals 8, and 4 to the power of x equals 26. So we know that these are exponential equations because the variable in all of them is located in the exponent. So if I were to ask you to find the value of x for each of the equations, the first and the second of them are going to be pretty straightforward because 16 is a perfect square of 4 by doing 4 squared. 2 raised to the third power gets us 8. But what about the third equation? If I have 4 to the x power equals 26, well, what power of 4 is going to get us 26? I don't know. I can't answer that right off the top of my head. And so that is one reason that we're going to start talking about logarithmic functions, because exponential functions have this special property where they are one-to-one, which means that if you look at a graph of an exponential function. So let me just draw one for you really quickly. So here is an example of an exponential equation. I can see that any vertical line that I draw through my graph is only going to go through one point in my curve that I've drawn. And so therefore it's one-to-one. Every input x has one output y. And because of that, it has an inverse function. And the inverse of an exponential function is a logarithmic function. And because of this relationship, we're allowed to convert between the two different forms of an equation. So here in the table, I have an example of a logarithmic function and an exponential function and how you would write one in terms of the other. So for example here, we have log base b of x is y. And then for our exponential function, it's b to the power of y is equal to x. So the answer to a logarithmic equation is going to give us an exponent, as you can see from the conversion between these two forms. Y is the answer of our log function, and it is also the power in our exponential function. So we can solve that before problem of 4 to the x power equals 26 by converting it to a log form. So let's go ahead and do that. So we have, and I'm going to use different colors to help us see what part goes where, 4 to the x power equals 26. And so if I want to write this in log form using that table that we have above, this can be written as log base. Well, our base in our exponential equation was 4. So log base 4 of what we're taking the log of. X is the answer of our exponential equation. So that's going to be 26 equals our exponent of our exponential function. So that will be x. So now we have solved our equation. We have found that the value of x is equal to log base 4 of 26. Now, as we're going through and solving our different logarithmic and exponential functions, there are two things that we need to know, and those are some special logarithms. So we have something called the common log, which is log base 10, and you'll see most likely it'll be denoted with just the word log. And this is the log button that you see on your scientific calculator or on like the Desmos calculator. Those are all the common log or log base 10. The other one that we're going to look at is natural logarithms. And those are log base e, but they will most commonly be written as ln. And again, that's the button that you would see on a standard calculator is ln. Now, these logarithms have some special properties. And so I've written them using the common log on the left-hand side and the natural logarithm on the right-hand side. So log of 1 is equal to 0. Same with the natural log of 1 equals 0. And we know this because if we think about this exponentially, converting between the two, well, this would be, well, let's do the natural logarithm. So this would be, our base is e, to the 0th power is 1. And we know that's true because any non-zero number raised to the 0th power is always 1. So this first property should make some intuitive sense. The second property is that log of 10, or the natural log of e, are equal to 1. And here, this should also make sense because we have a base of e raised to the first power should equal e, according to the statement. And that's true. Again, anything raised to the first power is always going to be itself. The third property, very similar. So we have log of 10 to the x power equals x, or the natural log of e to the x power is equal to x. And again, if we convert this to exponential form, this would be a base of e raised to the x power equals e to the x power. And this is in fact true. And then the last one is that 10 to the power of log of x is equal to x, as well as e to the power of the natural log of x is equal to x. And what this is really showcasing is the inverse properties of the two functions, exponential and logarithmic. So you can think of it as an exponent undoes the log. So same thing for both natural and common logarithms. So let's go ahead and talk about steps that we would take to solve these different types of equations. So first, we're going to look at using logarithms to solve exponential equations. So for example, we could think of that equation that I had above. So 4 to the x power equals 26. So the first thing that we're going to want to do is isolate the exponential expression. So in this case, our exponential expression would be 4 to the x power because that is the term that has the variable in the exponent. Step 2, you're going to take the common logarithm on both sides of the equation if it's base 10. If not, you're going to take the natural logarithm on both sides of the equation for bases other than 10. So I have some examples here listed. So in this first example, we have 10 to the x power equals 3. Well, our base of our exponent there is 10. So we would want to take the common logarithm on both sides as shown. Below, though, our example is 2 to the x power equals 7. And in this case, we have a base of 2. And so we want to take the natural logarithm on both sides as shown. Step 3, you're going to simplify using one of the properties in that table that we just went over above. And then lastly, we're going to solve for the variable. So first thing is, in order to use these steps, we need to understand when we use this, what types of equations we're looking for. And so this is going to be used if we have an exponential equation, so there's no log or natural log written anywhere in our equation, and we want to use logarithms to get the variable out of the exponent. Then we can solve the equation as we have in the past with our linear and quadratic and rational and other equations that we've talked about in the past. All right, so let's go ahead and look at an example. So here we're asked to solve the equation 2 times e to the 3x minus 1 power minus 5 equals 11. So I'm going to rewrite this a little bigger. So remember that the first step was we want to isolate our term with the exponent that contains our variable. So the first thing I'm going to do is get rid of this minus 5. So we're going to add 5 to both sides. And we get 2 times e to the 3x minus 1 power equals 11 plus 15 is 16. Sorry, 11 plus 5. And then we still have our term being multiplied by 2, so we can go ahead and divide by that. on both sides, and we get e to the 3x minus 1 power equals 8. So now we have our term e raised to our exponent with our variable in there by itself. So now the next step was we are going to take the either common log or natural log of both sides. And in this case, it makes the most sense to take the natural log since our base is e. So go ahead and do so. And when we do, what happens by using that third property from our table is that now we are left with just the exponent. So this natural log and the e kind of cancel each other out. So we have 3x minus 1 equals the natural log of 8. Again, that's by applying that power from the table. Then we're going to solve for our variable just like we would any other equation we've seen in the past. So now, in order to get x by itself, I first need to get rid of this minus 1 by adding 1 to both sides. One thing to be careful of here is that I'm not adding 1 to the 8 because I'm not taking the natural log of this 1. I'm only taking the natural log of this 8. So this plus 1 is on the outside. And then to undo this multiplication by 3, we're going to divide by 3 on both sides. And so we end up getting x equals the natural log of 8 plus 1 divided by 3. And if you evaluate this in a calculator, you should get a value of approximately 1.03. And there we have solved for x. And as always, if you're unsure about the steps that you've taken, you can always plug in your value for x back into this original equation and see, do you get 11 as an answer? All right, let's go ahead and look at using the definition of a logarithm to solve logarithmic equations. So here we have 4 steps. First thing is that we need to express the equation in the form of log base b of m equals c. Step 2, you're going to then use the definition of a logarithm to rewrite the equation in exponential form. So if we have log base b of m equals c, then in exponential form, that's going to be a base of b to the c power equals m. You're then going to solve for the variable. And then lastly, you're going to check the proposed solutions in the original equation. And make sure that you include in the solution set only values for which our m, or what we're taking the log of, is bigger than 0. If you'll recall from a previous video, we cannot take the log of a negative number, as the negative numbers are not included in the domain of logarithms. All right, so when do we use this? If we have a logarithmic equation, so in other words, if we see log or ln in our equation, we're going to use this to rewrite in exponential form and then solve the equation just like we've done in the past. So let's go ahead and look at an example. So here we are asked to solve log base 2 of the quantity x minus 1 equals 4. So the very first step said to put it in the form of log base b of m equals c, and our equation is already given to us in that way. So now our next step is to rewrite this in exponential form. So remember, our base is 2, so that's going to be the base of our exponential. The answer of our log is going to be our exponent, and then what we're taking the log of is our answer here. So there we have rewritten it in exponential form. Now we have an evaluation that we can do. So we can calculate 2 to the 4th power, and that's going to be 16. And now I'm just going to solve for x like normal. I want to get it all by itself, so I need to undo this minus 1 by adding 1 to both sides. So we get 17 equals x. Now in this case, we need to double check and make sure in our original equation if x equals 17 satisfies this statement. So let's go ahead and check. So we have log base 2 of x minus 1 equals 4. I'm going to replace my x with my solution of 17. And remember, since I am checking this, I am not going to mess with the right-hand side because I'm trying to see, does this left-hand side equal what we're trying to get of 4? So we can evaluate 17 minus 1 is 16. And then we know that log base 2 of 16 is the same thing as thinking of this problem as 2 to what power gets us 16. And in this case, this is going to be 4. So we get a true statement. Therefore, x equals 17 is our solution. So be sure that when you are solving these equations, you're first identifying the type of equation you are solving correctly. So like I said, if it is an exponent that contains a variable, then you're going to do the first method. If it is a log or ln that's seen in your equation, you're going to use the second method. Then you're going to apply the properties of logs and the definition of logarithms to solve for the variable. I hope you find this video helpful.